What if I told you that the universe isn't just an endless expanse of stars and galaxies, but something far more mysterious, a cosmic structure with a definite shape, a geometry so profound it defines reality itself? For thousands of years, some of the greatest minds in history have grappled with this very question, coming within a hair's breadth of the answer, only to watch it vanish like a star fading at dawn. Think about that for a moment. Centuries of effort, genius, and near misses, all leading toward one of the most fundamental truths about existence. This isn't just a story about science. It's a deeply human saga of curiosity, perseverance, and the tantalizing thrill of almost knowing. In this video, we're going to retrace 25 of those breathtaking near discoveries, each one a chapter in an epic quest to understand the shape of the cosmos. From the ancient Greeks gazing at the heavens with nothing but naked intuition to today's physicists parsing data from space telescopes, we'll explore how close we've come, again and again, to unlocking the geometry of everything. You'll witness moments of brilliant insight overshadowed by simple oversights, cultural assumptions that blinded generations, and mathematical clues that sat unnoticed for decades, all because seeing the true shape of the universe demands more than equations or observations. It requires us to reimagine reality itself, so prepare to step into a journey across time and thought, where each twist and turn brings us closer to a revelation that has eluded us for millennia. You'll come away not only with a deeper appreciation of how science stumbles toward truth, but with a renewed sense of wonder at the cosmos and our place within it. This is more than a history lesson. It's an invitation to see the universe and human ingenuity in a completely new light. From the earliest moments human beings looked up at the night sky, we have been trying to map not just the stars, but the very stage upon which they perform. This ancient obsession, this deep need to comprehend the architecture of everything, began not with telescopes and equations, but with pure, unaided observation and philosophical deduction. Picture an ancient Greek philosopher standing under a canopy of stars, trying to reason out the nature of the cosmos based on the simple, perfect shapes he saw in the world around him. To thinkers like Aristotle, the most logical and divine shape was the sphere, a form without beginning or end, eternal and harmonious. It made perfect sense to them that the universe itself would be a series of nested, crystalline spheres, with our stable, unmoving Earth sitting serenely at the absolute center of it all. This geocentric model was a breathtakingly elegant and self-contained system, offering a comforting sense of order and place. It told a story of a cosmos designed with humanity at its heart, a notion that would resonate for centuries. But this beautiful model was built on a foundation of assumptions that were, while reasonable for the time, ultimately incorrect. The tools to test these ideas simply didn't exist yet. They couldn't measure the incredible distances to the stars or detect the subtle parallax shift that would have hinted at Earth's motion. Their mathematics, largely based on Euclid's geometry of flat, infinite planes, was not equipped to describe a curved or dynamic reality. So for over 1,000 years, this Earth-centered, spherical universe was the accepted truth, a testament to how a compelling narrative can sometimes overshadow the need for empirical proof. It was a monumental first draft of cosmic understanding, a necessary stepping stone that, despite its flaws, established the very practice of modeling the heavens. The real turning point began when that comfortable model started to show cracks. The Renaissance didn't just rebirth art and culture, it ignited a revolution in thought that extended to the stars. Armed with new mathematical tools and a growing courage to question authority, visionaries like Copernicus dared to suggest the unthinkable. what if we are not the center of everything? His heliocentric model was a radical departure, a profound demotion for humanity that simultaneously offered a far simpler explanation for the perplexing retrograde motion of the planets. Yet, even this colossal leap forward was still trapped within the old paradigm of perfect circles and a finite celestial sphere. Copernicus replaced the Earth with the Sun at the center, but kept the universe enclosed, unable to break free from the philosophical and geometric constraints of his predecessors. This pattern of building upon the past while being limited by it is the defining heartbeat of our story. Each generation of thinkers stood on the shoulders of giants, yet often found themselves peering through the same conceptual lenses, their vision narrowed by the very knowledge they inherited. They had the pieces of the puzzle, but the overall picture of a curved, expanding, or even multiply-connected universe was so far outside their experience that it remained unimaginable. The true geometry of space was hidden in plain sight, waiting not just for better observations, but for an entirely new way of thinking about space itself. These early struggles were not failures. They were the essential, arduous first steps in a marathon of discovery, each one bringing us incrementally closer to glimpsing the profound and mysterious shape of our cosmic home. And so we arrive at our first great near miss, a moment where the path toward understanding the universe's shape forked, and for centuries we took the wrong turn. It all began with two towering intellects in ancient Greece, working just a generation apart, who laid down two completely different and ultimately incompatible visions of space itself. First came Euclid around 300 BCE, whose book, The Elements, wasn't just a math text, it was a declaration that space was flat, infinite, and followed a strict, logical set of rules. His geometry of parallel lines that never meet and triangles whose angles always add up to exactly 180 degrees described a stage that was vast, empty, and fundamentally unchanging. It was a powerful and elegant system, but it was just a description of an abstract space, not necessarily our physical reality. Then came Aristotle, who looked at the same world and saw something entirely different. He wasn't content with abstract math. He wanted a physical model, a tangible cosmos, observing the perfect curve of the moon's shadow during an eclipse and the way stars seemed to sweep in great circular arcs across the night sky. He became convinced the universe itself must be a sphere. A finite, contained, and beautifully ordered sphere with our planet sitting motionless right at its absolute center. This wasn't just a guess to him. It was the only logical conclusion. The sphere was the most perfect shape, and a perfect divine universe would naturally take that form. His model was a work of philosophical art, a cosmic onion with layers of crystalline spheres holding the moon, the sun, the planets, and finally the fixed stars, all rotating around us in a harmonious, eternal dance. But here is where the miss occurs, a subtle oversight with monumental consequences. Aristotle's model was built for comfort and order, not for scientific rigor. It provided an answer that felt right, but it couldn't withstand questions he never thought to ask. For instance, if Earth is moving, even just rotating, then the positions of the nearby stars should appear to shift slightly against the background of more distant stars, an effect called stellar parallax. Aristotle didn't see this shift, but that's because the stars are immeasurably farther away than he could have possibly conceived. His instruments weren't precise enough to detect such a tiny change, so he took the absence of evidence as evidence of absence, concluding that Earth must therefore be stationary. It was a classic case of not having the right tools to see the truth. Even more critically, his geometry was a prison. By envisioning a finite sphere, he closed off the mind to other, far more bizarre and wonderful possibilities. The very idea of a non-Euclidean cosmos, one where space could be curved like a saddle or a balloon, where parallel lines might eventually cross or spread apart forever, was utterly unimaginable within his philosophical framework. His universe was a finished product, static and complete. He missed the clues not because he was unobservant, but because his cultural and philosophical biases acted like blinders. The desire for a perfect, centered, and human-focused cosmos was so strong that it prevented him from considering a reality that was vast, dynamic, and utterly indifferent to our place within it. This first near miss set a pattern that would repeat for 2,000 years. The compelling allure of an elegant, comforting idea can be the biggest obstacle to discovering a more complicated, but far more Chinese letter truth. Building on Aristotle's spherical cosmos, a brilliant thinker in 2nd century Alexandria named Claudius Ptolemy took the next great step. He saw a problem with the model. While beautiful in theory, it couldn't accurately predict the strange, looping paths of the planets as they occasionally seem to reverse course in the sky, a motion we call retrograde. Ptolemy was a master of detail, an astronomer obsessed with making the numbers match the heavens. His great work, the Almagest, wasn't a philosophical treatise. It was a practical manual for prediction, and his solution was a work of geometric genius. He introduced a system of epicycles and deference imaginary circles upon circles. A planet would travel on a small circle, the epicycle, whose center itself traveled on a larger circle, the deferent, around the Earth. This complex celestial clockwork, with its intricate loops and turns, could reproduce the observed planetary motions with remarkable accuracy for its time. But this very success became its greatest failing. In his quest for precision, Ptolemy doubled down on Aristotle's core assumptions. He cemented the idea of a fixed, unchanging celestial sphere that held the stars, a perfect and immutable boundary to the universe. This assumption was the anchor of his entire system, and it was this anchor that would hold back human thought for over a millennium. Because the model worked so well for practical purposes like creating calendars and predicting positions, it became the definitive word on cosmology. To challenge Ptolemy was to challenge observable success, and for generations no one had a good enough reason to do so. His near miss lies in this triumph of utility over truth. He was so focused on perfecting the mechanics of a geocentric universe that he never stopped to question whether the stage itself, the very fabric of space, could be something other than a static, finite arena. The clues were there, hidden in his own complex equations. All those epicycles were essentially mathematical fudges, clever corrections for an underlying flaw in the model. They were the result of trying to force circular motion onto paths that were fundamentally not circular, all because of the deep-seated belief that the heavens must be perfect, and therefore only perfect circles were allowed. This adherence to philosophical beauty over geometric simplicity created a Rube Goldberg machine of the cosmos, incredibly complex yet built on a foundation of sand. Furthermore, by assuming the starry sphere was fixed and final, Ptolemy closed the door to any speculation that the universe might be dynamic, that it could be expanding, contracting, or curved in ways his tools could not measure. He had no concept of gravity warping space or of a cosmos without a center, ideas that would require a completely new physics. His legacy, therefore, is a profound paradox. Ptolemy's Almagest was one of the most successful scientific works in history, used for over 1,400 years, yet its success fossilized cosmological thought. It provided answers that were good enough, and in doing so, it extinguished the questions that might have led to a deeper understanding far sooner. This is the perennial danger of a theory that is empirically successful but philosophically constrained. It creates a comfort zone that is incredibly difficult to escape. The pursuit of better predictions within a flawed model can sometimes be the biggest obstacle to discovering a better model altogether. Ptolemy gave the world a fantastically accurate map of a universe that didn't exist, and it would take a revolution to tear that map down and start drawing a new one from scratch. For over 1,000 years, Ptolemy's Earth-centered universe reigned supreme, a complex but trusted map of the heavens. Then, in the 16th century, a quiet Polish canon and astronomer named Nicolaus Copernicus performed one of the most profound thought experiments in human history. He dared to ask a simple, heretical question: what if we've had the center wrong all along? His answer, detailed in his revolutionary book on the revolutions of the heavenly spheres, was a stunning paradigm shift. He placed the Sun at the center of it all, with Earth demoted to just another planet orbiting it. This single change didn't just move celestial bodies, it moved humanity itself, tearing us from our privileged place at the heart of creation and setting us adrift in a cosmos that no longer revolved around us. The brilliance of the Copernican model was its elegant simplification. Those perplexing loops of retrograde motion, which required all of Ptolemy's cumbersome epicycles to explain, suddenly made perfect sense. They were an illusion, a simple consequence of Earth itself moving faster than the outer planets, overtaking them like a faster car on a cosmic highway, and making them appear to slide backward against the backdrop of stars. It was a geometric masterstroke, cutting through centuries of complexity with a cleaner, more logical arrangement. This was the monumental breakthrough, the crack in the dam of ancient thought that would eventually unleash a flood of new discovery. Yet, for all its revolutionary power, Copernicus's vision was still trapped within the same old cosmic box. He had swapped the central body from Earth to the Sun, but he held fast to the ancient, deeply ingrained belief that the universe was a finite sphere, bounded by a shell of fixed stars. His space was still the flat, absolute, and infinite void described by Euclid's geometry. He never once considered that the fabric of space itself could be curved, warped, or have a more exotic topology. His mind was focused entirely on the mechanics of orbits, on getting the planets to move correctly around a new center. The deeper, more radical question of the stage upon which this drama played out, its overall shape and structure, remained not only unanswered but unasked. This is the core of his near miss. Copernicus possessed the intellectual courage to challenge the central dogma of cosmology, but he lacked the tools and the framework to challenge its geometry. He was a mathematician and an astronomer, not a physicist who could conceive of gravity bending space or a philosopher who could imagine an infinite, centerless universe. He was working within the paradigm of his time, using the same circular orbits and perfect spheres that the ancients revered, simply arranging them around a new focal point. His work was a necessary and brilliant half-step, a crucial leap forward that nonetheless stopped short of the finish line. It solved the immediate puzzle of planetary motion, but left the far grander mystery of cosmic architecture completely untouched, a testament to how even the most revolutionary thinkers can be blinkered by the unspoken assumptions of their age. And so the torch passed from the quiet theorist to the fiery experimentalist. Just decades after Copernicus's book stirred the pot, an Italian mathematician named Galileo Galilei did something that would change astronomy forever. He pointed a new invention, the telescope, toward the night sky. What he saw didn't just challenge the old models, it systematically dismantled them. Where others had reasoned and calculated, Galileo simply looked, and in doing so, he witnessed a universe far stranger and more dynamic than anyone had dreamed. He saw 4 moons circling Jupiter like a miniature solar system, a direct challenge to the idea that everything must orbit the Earth. He observed the phases of Venus, which cycled from a thin crescent to a full disk exactly as predicted by the Copernican model. but utterly impossible in Ptolemy's Earth-centered arrangement. And perhaps most stunningly, he gazed upon the Milky Way and saw it resolve from a faint smear of light into a vast, countless multitude of individual stars, revealing a cosmos of unimaginable depth and scale. Each of these discoveries was a hammer blow to the Aristotelian and Ptolemaic worldview. The heavens were not perfect and unchanging. They were littered with imperfect moons and mountains, and they contained a number of stars so great it defied the very notion of a finite, contained sphere. Galileo's observations provided the first direct, irrefutable evidence that Copernicus had been right. The Earth moved, and it was not the center of all things. This was a seismic shift in human thought, a triumph of observation over dogma. Yet, for all his revolutionary seeing, Galileo's interpretation of what he saw remained trapped within a familiar geometric box. He used these stunning new facts to argue for a sun-centered system, but he still imagined that system playing out on an infinite, flat Euclidean stage. The universe was now bigger, but its fundamental geometry was still, in his mind, the passive and absolute void described by ancient thinkers. This is the heart of his near miss. In shattering the crystal spheres, Galileo inadvertently embraced a different kind of prison, the prison of infinite, flat space. He never considered that the fabric of this vast new universe might itself be curved, warped, or bounded in some non-Euclidean way. His telescope could reveal new objects and new motions, but it could not measure the subtle curvature of space itself. He was so focused on winning the battle against geocentrism that he didn't see the next, even larger war on the horizon, the war to understand the true shape of the cosmic arena. His work provided all the ammunition needed to destroy the old model, but it offered no new geometry to replace it. He proved we were on a stage that was much, much larger, but he never questioned whether the stage itself was flat or curved. This highlights a recurring theme in scientific discovery. New tools can reveal stunning new data without immediately providing the new concepts needed to interpret that data fully. Galileo's telescope was a key that unlocked one door, but it revealed a hallway with many other locked doors he didn't even try to open. His mind, brilliant as it was still shaped by the prevailing mathematical and philosophical ideas of his time. The very success of his observations in supporting Copernicus may have ironically reinforced his commitment to a simpler, Euclidean cosmology. He had fought so hard to prove the Earth moves around the Sun. The idea that space itself might be dynamic and participative would have seemed like a bridge too far. His legacy, therefore, is a powerful mixture of revolutionary breakthrough and profound limitation. He gave us the eyes to see a new cosmos, but he left it to the mathematicians who followed to provide the mind to truly understand its shape. While Galileo was training his telescope on the heavens, a German mathematician named Johannes Kepler was staring at reams of data, convinced that hidden within the meticulous observations of his mentor, Tycho Brahe, was a secret key to the cosmos. Where Galileo was a master of observation, Kepler was a master of mathematics and mystical intuition. He was obsessed with finding geometric harmony in the solar system, and his breakthrough was nothing short of revolutionary. After years of painstaking calculation, he made a discovery that shattered a 2,000-year-old tradition. The planets, he declared, do not move in perfect circles. Their paths are ellipses, with the Sun occupying one of the two focal points. This was his first law, a monumental departure from the Platonic ideal of celestial perfection. His second and third laws were equally profound, establishing precise mathematical relationships between a planet's orbital speed and its distance from the Sun. For the first time, the solar system was revealed not as a collection of divine, unpredictable wanderers. but as an intricate clockwork mechanism governed by mathematical rules. This was a giant leap toward a dynamical understanding of the universe, a system in motion governed by physical laws. Kepler even speculated about a physical force emanating from the sun that pushed the planets along, a primitive but prescient notion of what would later become gravity. He was peering right into the mechanics of the cosmos, coming tantalizingly close to a concept of universal physical interaction. Yet, for all this visionary thinking, Kepler's imagination hit a firm, invisible wall when it came to the universe as a whole. He could mathematically describe the elliptical dance of the planets, but he still pictured them performing inside a vast, dark, spherical shell, the ancient sphere of fixed stars. In his mind, this starry sphere was the final boundary of creation, a finite container for God's grand design. This belief fundamentally limited him. Because he saw the stars as a static backdrop, a literal wall at the edge of everything, he never considered that the force he imagined pushing the planets might also govern the stars themselves. He lacked the crucial insight that gravity could be a universal force, acting over immense distances to sculpt the large-scale structure of everything that exists. This is the core of his near miss. Kepler had unlocked the rules for the local dance, but he failed to see that the entire ballroom itself might have a shape dictated by those same rules. His laws described how objects moved within space, but he never pondered that space itself could be an actor in the drama, that the gravitational force he intuited might actually warp and curve the very fabric of the universe, influencing its overall geometry. His worldview, though revolutionary in part, was still classical and finite. It was a cosmos with a center and an edge, a contained system that couldn't accommodate the mind-bending concepts of an infinite universe, or a curved one, or one that was expanding or contracting. He was a bridge between the mystical past and the scientific future, but he got stuck in the middle. His brilliant mathematical tools rendered powerless to ask the biggest question of all: what is the shape of the stage? If Galileo gave us the eyes to see the cosmos and Kepler gave us the mathematical rules for its local dance, then it was Isaac Newton who, in 1687, provided the music, a universal force that governed the motion of everything, from a falling apple to the orbit of the moon. His monumental work, the Principia Mathematica, was arguably the greatest scientific achievement of its age. In it, he laid down his law of universal gravitation, a single, breathtakingly simple equation that could predict the gravitational pull between any two objects in the universe. Suddenly, the chaotic heavens were revealed to be a realm of perfect, predictable order, running like a divine clockwork machine according to immutable mathematical laws. It was a unification of physics that brought the cosmos to heel, explaining not just elliptical orbits but the tides, the precession of the equinoxes, and the trajectories of comets. Yet for this cosmic force to work its magic, Newton needed a stage, and the stage he envisioned was absolute space. To him, space was not an active participant in the drama of physics. It was an infinite, rigid, unchanging, and utterly passive container, a fixed and immovable arena modeled precisely on the flat, Euclidean geometry of the ancients. It was an absolute reference frame, the unmoved mover against which all true motion could be measured. Time, similarly, was an absolute, universal tick-tock that flowed at the same rate for everyone, everywhere. This concept of an absolute stage was the invisible foundation upon which his entire theory of gravity was built. It was so intuitive, so seemingly obvious, that it went almost entirely unquestioned. This is where Newton's profound near miss lies. He had discovered the force that bends the paths of planets, but it never occurred to him that this same force might be bending the very fabric of the stage itself. He treated gravity as a mysterious, invisible force acting instantaneously across the vast emptiness of space. but he never asked what that space was made of, or how the presence of mass might alter its very nature. The idea that space and time could be malleable, that they could warp and curve in response to matter and energy, was a conceptual leap too far for even his genius. He separated the actor, gravity, from the stage of space, and in doing so, he missed the chance to see that they were one and the same. The success of his framework became its own greatest obstacle. Newtonian mechanics was so spectacularly powerful at predicting observable phenomena that it effectively deterred anyone from questioning its underlying assumptions for over 200 years. Why would anyone poke at the foundations of a palace that was so magnificent and sturdy, even when cracks began to appear, like the tiny, unexplained wobble in the orbit of the planet Mercury that didn't quite match Newton's predictions? Most scientists assumed the problem was with our observations or with some unseen planet, not with the fundamental nature of space and time. The law was considered so perfect that anomalies were seen as puzzles to be solved within the Newtonian system, not as clues that the system itself might be flawed. Newton's legacy, therefore, is a masterpiece with a critical blind spot. He gave us the universe's script but misunderstood the geometry of the theater. His work cemented a worldview of a flat, static, infinite space, a concept that would dominate science for centuries and actively delay the consideration of curved or dynamic cosmologies. It took the unparalleled imagination of an Einstein to finally realize that the stage isn't just a backdrop. It's a flexible, dynamic participant, and gravity isn't a force pulling through space, but the shape of space itself, guiding everything along its curves. Newton came closer than anyone before him to a complete description of reality, but his unquestioning faith in an absolute Euclidean stage meant the true, warped shape of the universe remained hidden in plain sight. In the early 1800s, as astronomers were mapping the heavens with ever greater precision, a German physician and amateur astronomer named Heinrich Olbers pondered a simple question with staggering implications: why is the night sky dark? On the surface, it seems trivial. Of course, the sky is dark at night. But Olbers, trained in an era steeped in Newtonian ideas of an infinite, static universe, realized this everyday observation was actually a profound paradox. He reasoned that if the universe were truly infinite and filled with an endless number of stars, then in every direction you looked, your line of sight would eventually land on the surface of a star. Just as in a dense, ancient forest, you eventually see a tree trunk in every direction, the sky should be a solid, blinding sheet of starlight, as bright as the surface of the sun. The fact that it isn't, that we instead see a mostly black void punctuated by points of light, meant something was fundamentally wrong with the prevailing model of the cosmos. This was not just a quirky thought experiment, it was a direct challenge to the scientific consensus. The brightest minds of the era, including Newton himself, had envisioned a universe that was infinite in both space and time, with stars scattered uniformly throughout. Olbers' paradox, as it came to be known, should have been the clue that shattered this image. It pointed toward only a few possible solutions. Either the universe is not infinite but finite in size, or it is not static but dynamic and evolving, or perhaps the light from the most distant stars is somehow being absorbed or reddened before it can reach us. Any one of these conclusions would have been a revolutionary leap forward in cosmology. Yet, for the most part, the scientific community of the 19th century dismissed it. They lacked the conceptual framework to take it seriously. The idea of a universe with a beginning, or one that was expanding, seemed more like theology than science. Without Einstein's theory of general relativity, which would later show how space itself can stretch and warp, they had no language to describe a dynamic cosmos. Without the concept of an expanding universe, They couldn't realize that the light from the most distant galaxies is stretched into the invisible infrared part of the spectrum, robbing it of its energy and preventing the sky from blazing with light. And without a firm grasp of the immense, finite age of the universe, they couldn't understand that we only see the light from stars within a certain cosmic horizon. Light from stars beyond that distance hasn't had time to reach us yet. This collective shrug represents a spectacular near miss. The answer to the universe's large-scale structure was hiding in plain sight, encoded in the simple darkness between the stars. Olbers had handed them a key, but they didn't know what door it unlocked. Instead of questioning their fundamental assumptions about infinity and stasis, they largely filed the paradox away as an unsolved curiosity, a minor annoyance in an otherwise successful Newtonian worldview. This delay had real consequences. It meant that the revolutionary ideas of a curved, expanding, or finite-aged universe would have to wait another century for a physicist who was willing to question absolutely everything. The darkness of the night sky, which we now know is profound evidence for a dynamic cosmos with a beginning, remained a mystery because the tools to solve it were not in the toolbox. It stands as a powerful lesson that sometimes the most important clues are the ones we train ourselves not to see. While the philosophers and astronomers were wrestling with the darkness between the stars, a different kind of genius in Germany was contemplating the very ground beneath his feet, asking a question so radical it bordered on heresy. What if the ancient geometry of Euclid, the foundation of all mathematics for over 2,000 years, was not the true geometry of our world? Carl Friedrich Gauss, a man so brilliant he is often called the Prince of Mathematicians, dared to entertain this possibility. He had been developing a new, non-Euclidean geometry where parallel lines could eventually meet, and the angles of a triangle might not add up to 180 degrees. But for Gauss, abstract math was not enough. He needed to test it. He needed to measure the physical universe itself. So, in the early 1800s, he devised an astonishingly clever experiment. He selected 3 mountain peaks in Germany, the Brocken, the Hohenhagen, and the Inselsberg, and using light beams and precise surveying equipment, he meticulously measured the angles of the giant triangle they formed. His goal was breathtakingly simple yet profound. If the sum of those 3 angles was greater than 180 degrees, it would indicate the universe had positive curvature, like a sphere. If it was less, it would suggest negative curvature, like a saddle. This was not just a survey, it was a direct probe into the fundamental geometry of reality, an attempt to use the tools of earth-bound measurement to divine the shape of the cosmos. The results, however, were disappointingly ordinary. The angles added up to 180 degrees, just as Euclid had always said they would. On the surface, it seemed like a validation of the old ways. But Gauss's experiment was a near miss of a deeply tragic kind. He had the right idea, but he was simply working on too small a scale. The curvature of space, as described later by Einstein's general relativity, is incredibly subtle. The mass of the Earth, or even of entire mountain ranges, warps space-time only by a minuscule amount, far too small to be detected with the surveying instruments of the 1800s. Gauss was trying to measure the curvature of a continent when he needed to be measuring the curvature of the entire solar system, or even the galaxy. His experimental setup, while brilliant, was like using a ruler to measure the roughness of a single grain of sand, and then concluding the entire beach is perfectly smooth. The real tragedy, however, was not the null result. It was the intellectual isolation that followed. Gauss was so far ahead of his time that he had no one to share his revolutionary thoughts with. He confided in a friend that he feared the clamor of the Boeotians, a reference to the ancient Greeks' term for simple-minded people. if he were to publicly suggest that Euclidean geometry might not be the absolute truth. Without a supportive theoretical framework that connected geometry to physics, his daring experiment was seen as little more than a quirky, if precise, surveying project. It didn't spark a new field of physics or inspire a generation of cosmologists because the scientific community lacked the context to understand its profound implications. The link between the abstract mathematics of curvature and the tangible force of gravity had not yet been forged. This moment stands as a heartbreaking what-if in the history of science. Imagine if Gauss had possessed the technology of a modern satellite or the theoretical insight of Einstein. He might have become the father of both non-Euclidean geometry and general relativity a century early. His near miss underscores a critical lesson. A pioneering idea, no matter how brilliant, requires more than just one genius to flourish. It needs a community ready to listen, technology capable of testing it, and a web of other ideas to connect to. Gauss had the vision to ask the question, but the world was not yet equipped to help him find the answer. His lonely experiment became a quiet footnote, a path not taken, while the mathematical tools he helped create continued to develop in the abstract, waiting for a physicist who would one day use them to build a new cosmology. Meanwhile, in the quiet halls of a university in Germany, a shy and brilliant mathematician was laying the intellectual groundwork that would, decades later, make Einstein's revolution possible. In 1854, a young Bernhard Riemann delivered a lecture that was so radically abstract his contemporaries struggled to grasp its significance. He wasn't an astronomer peering through telescopes or a physicist experimenting with forces. He was a pure mathematician, and he was about to reinvent the very concept of space itself. His mission was to generalize geometry, to break it free from the flat, two-dimensional plane it had been trapped on since the time of Euclid. What he created was a breathtakingly flexible new system, a mathematics that could describe space not just in 2 or 3 dimensions, but in any number of dimensions, and most importantly, space that could be curved. Riemann's geometry was a universe of possibilities. He provided the equations to describe a space where parallel lines could converge or diverge, where the angles of a triangle could add up to more or less than 180 degrees, and where the very notion of a straight line was replaced by the geodesic, the shortest path between 2 points on a curved surface. This was the precise mathematical language needed to describe a cosmos that was warped and molded by mass and energy. In essence, Riemann had invented the toolbox for general relativity half a century before Einstein would need it. He had provided the vocabulary to describe a spherical universe, a saddle-shaped universe, or a universe with a truly bizarre topology, all with rigorous, beautiful equations. Yet, in a heartbreaking repeat of the pattern we've seen so often, this monumental breakthrough remained almost entirely within the realm of abstract mathematics. Riemann himself was in poor health and died young, and he never attempted to apply his radical new geometry to the physical world. He saw it as a branch of pure mathematics, an exploration of logical possibilities, not a practical description of reality. And the physicists of his era, for the most part, ignored it. They were still utterly enthralled by the Newtonian world machine, which ran perfectly on a flat Euclidean stage. The idea that the space we live in might not be flat seemed not just wrong but ludicrous, a fanciful speculation with no connection to the real world they were measuring and testing. This created a chasm between mathematical innovation and physical application that would stall cosmology for decades. Here was the complete, ready-made mathematical framework to model a curved cosmos, sitting on a shelf, gathering dust, while astronomers continued to collect data that could have been reinterpreted through its lens. Unexplained anomalies in planetary orbits, the mysteries of stellar motion, even Olbers' paradox, all of them were puzzles waiting for the key of curved space-time. But because the physics community wasn't looking for that key, the puzzles remained unsolved. The near miss here is particularly poignant because it wasn't a failure of observation or an error in calculation. It was a failure of imagination and communication between disciplines. The mathematicians had built a new world, but the physicists were too comfortable in the old one to take a tour. Riemann's work became a classic example of an idea arriving too soon, a seed falling on ground not yet ready to receive it. It would take the dual shocks of Einstein's revolutionary genius and the confusing results of experiments like Michelson-Morley to finally push physicists to desperation, forcing them to rummage through the attic of mathematics for tools that could save their theories. And there they would find Riemann's geometry, polished and waiting, the answer to a question they had only just learned how to ask. The tragedy is not that the tool didn't exist, but that it existed in plain sight for so long, unused, while science took a longer, more difficult path to the same inevitable destination. Meanwhile, across the North Sea in Scotland, a different kind of theoretical breakthrough was taking shape, one that would perfectly illustrate the tension between mathematical elegance and physical misconception. James Clerk Maxwell, a physicist with a poet's soul, was weaving together the disparate threads of electricity and magnetism into a single, breathtaking tapestry of equations. His work in the 1860s was nothing short of prophetic. He demonstrated that these two forces were not separate entities but different manifestations of a single electromagnetic force. And in a stunning leap of intuition, his math revealed something even more profound: that oscillating electric and magnetic fields could propagate through space as waves, and that these waves traveled at a specific, fixed speed that just so happened to be the known speed of light. In one elegant stroke, Maxwell had unified light itself with electromagnetism, predicting the entire spectrum of radiation from radio waves to gamma rays. But this magnificent intellectual achievement came with a conceptual baggage that would haunt physics for decades. The science of the day was dominated by mechanical thinking. Every wave known to humanity required a medium to travel through. Sound waves needed air, water waves needed water. It was unthinkable that a wave, especially one as fundamental as light, could travel through the utter emptiness of space. There had to be a substance, an invisible, frictionless, all-pervading material that filled the cosmos, acting as the substrate for these vibrations. They called it the luminiferous ether, and it was more than just a hypothesis. It was an article of faith, a necessary component to make this beautiful new theory fit within the comfortable, mechanical worldview of 19th century physics. This unquestioning acceptance of the ether was the seed of a spectacular near miss. Maxwell's equations were a complete and accurate description of reality, but their interpretation was shackled to an ancient concept. The scientific community, dazzled by the power of the math, immediately began a decades-long hunt for this elusive substance. The logic was simple. If the ether is a stationary medium through which light waves ripple, and Earth is moving through space, then we should be able to detect an ether wind blowing past us, just as a cyclist feels a wind on a still day. This ether wind should affect the speed of light measured in different directions. The stage was set for a definitive experiment, one designed to measure our planet's motion through this invisible cosmic ocean. The effort to find this proof culminated in 1887 with the meticulous work of Albert Michelson and Edward Morley. Their apparatus, an incredibly precise interferometer, was a masterpiece of experimental design, capable of measuring differences in the speed of light with astonishing accuracy. They split a beam of light, sent the parts racing perpendicular to each other, and brought them back together, expecting to see a telltale interference pattern caused by our planet's movement through the ether. The result, however, sent a shockwave through the physics community. They found nothing, no difference, no ether wind. The speed of light was perfectly constant in every direction, regardless of the Earth's motion. It was a monumental null result, a clean and undeniable zero that should have been the death knell for the ether concept. But here is where the near miss becomes truly profound. Faced with this stunning contradiction, many brilliant minds refused to abandon their cherished ether. Instead of seeing the null result as evidence that the ether didn't exist, they desperately tried to save it by inventing increasingly convoluted explanations. Perhaps objects contracted in length as they moved through the ether, exactly enough to cancel out the expected time difference in the experiment. The Irish physicist George Fitzgerald and the Dutchman Hendrik Lorentz independently proposed this very idea of length contraction. It was a clever mathematical fix, an ad hoc adjustment designed to preserve the old model. They were so close, Lorentz's equations, in particular, almost perfectly described the effects we now attribute to relativity. But they missed the revolutionary point because they were still thinking mechanically. They saw length contraction as a physical squeezing of atoms due to motion through a medium, a distortion of matter moving through absolute space. It never occurred to them that the null result was telling them something far more fundamental, that there is no absolute space, no preferred frame of reference, and that space and time themselves are relative and interwoven. They invented a complex reason why the experiment failed to detect the ether's motion, rather than accepting the simpler, more elegant truth that there was nothing to detect. This collective failure of imagination is a classic case of a paradigm's gravitational pull being too strong to escape. The ether was such an intuitively comfortable idea that letting it go seemed more absurd than inventing bizarre new physical properties to protect it. They were patching a leaky theory with mathematical duct tape when what they needed was a whole new foundation. The simpler, more profound solution was to discard the ether entirely and realize that Maxwell's equations were telling them the truth all along. Light is a wave that doesn't need a medium. The constant speed of light isn't a constant relative to the ether. It is a fundamental constant of the universe for all observers. This realization that space itself has geometric properties that dictate this constancy was the leap they couldn't make. They had the right math but the wrong metaphor, and it would take a young patent clerk unburdened by the dogma of the era to look at the same equations and the same null result and see not a problem to be fixed, but a doorway to a new reality. So the stage was set for a definitive confrontation. After decades of theorizing about the luminiferous ether, the scientific world had its best chance to prove its existence. In 1887, at the Case School of Applied Science in Cleveland, Ohio, Albert Michelson and Edward Morley assembled an instrument of breathtaking precision. Their interferometer was designed to catch the ether in the act. The principle was straightforward. If Earth is sailing through a stationary ether sea, then a beam of light traveling in the same direction as our orbit should be slightly slowed by the ether's current, like a swimmer moving against a gentle river. A beam shot perpendicular to that motion should be unaffected. By splitting a single light beam and sending the two parts racing at right angles to each other before reuniting them, their device could detect an infinitesimally small difference in their speeds. Everyone expected a clear signal, a definitive fingerprint of our planet's motion through the cosmic medium. The result was not just surprising, it was deeply unsettling. The experiment found nothing, no difference, no ether wind. The interference fringes in their viewfinder remained perfectly still, as if the entire apparatus were motionless in the universe. It was a monumental null result, a clean and undeniable zero that should have been the death knell for the entire concept of the ether. the most precise measurement of its kind had just returned a verdict that contradicted one of the most deeply held beliefs in physics. The scientific community was baffled. It was as if they had built the most sensitive seismograph ever conceived, placed it directly on a fault line, and felt not even the faintest tremor. Faced with this stunning contradiction, the reaction of many brilliant minds was not to question the existence of the ether, but to invent increasingly elaborate reasons why they had failed to detect it. The most famous of these salvage attempts came from physicists George Fitzgerald and Hendrik Lorentz. They independently proposed a radical idea: perhaps objects physically contract in length along the direction of their motion through the ether. This length contraction, they suggested, would exactly cancel out the time difference the interferometer was designed to measure. It was a brilliant mathematical fix, an ad hoc adjustment designed to preserve the old model at all costs. Lorentz even developed a set of transformations that beautifully described this effect. They were so close to the truth, yet they missed the revolutionary point entirely. They saw this contraction as a literal, physical squeezing of the atoms in the apparatus, a mechanical consequence of plowing through a resistive medium. They were trying to save the ether by making the universe seem strangely conspiratorial, perfectly designed to hide the very motion it was supposed to reveal. This collective failure of imagination is one of the most dramatic near misses in the history of science. They had the crucial clue right in front of them, the constant speed of light for all observers, but they interpreted it as a problem with their detection method, not a fundamental property of the universe itself. Their unwavering belief in absolute space and a material ether acted like intellectual blinders. The simpler, more elegant solution was to discard the ether entirely and accept that the speed of light is a universal constant because space and time themselves are not absolute and separate, but relative and interwoven. The null result wasn't a failure of the experiment. It was a success that pointed toward a reality far more strange and wonderful than anyone had dared to imagine. It was the first clear signal that the stage of the universe was not a fixed, absolute container, but something dynamic and participative. This reluctance to let go of a comforting, intuitive idea delayed the acceptance of relativity for nearly 2 decades, a poignant reminder that sometimes the hardest thing for science to overcome is not a lack of data, but a surplus of preconception. And so we arrive at the brink of the 20th century, a moment of exquisite tension in the world of physics. The Michelson-Morley experiment had delivered its baffling verdict, and the scientific community was scrambling for an explanation. It was into this intellectual ferment that the distinguished Dutch physicist Hendrik Lorentz stepped, armed with a set of equations that seemed to offer a way out of the crisis. Lorentz was a towering figure, a Nobel laureate deeply respected for his work in electromagnetism. He approached the problem not as a radical seeking to overturn the established order, but as a master craftsman trying to repair a beautiful, intricate clock that had suddenly developed a perplexing tick. His solution was both brilliant and, in hindsight, tragically conservative. He developed a set of mathematical formulas, the Lorentz transformations, that perfectly accounted for the null result. These equations described how, for an object moving through the stationary ether, its length would contract along the direction of motion, and time itself would dilate or slow down. The math was impeccable. It showed that the reason Michelson and Morley couldn't detect the ether wind was because their apparatus had physically shrunk by just the right amount to cancel out the expected time difference. It was a fix of breathtaking precision, a mathematical patch that saved the cherished concept of the absolute, motionless ether. But here lies the core of the near miss. Lorentz never saw his transformations as revealing a fundamental truth about the nature of reality. To him, length contraction wasn't a property of space and time themselves. It was a mechanical effect caused by the interaction of electromagnetism with matter. He believed the forces holding atoms together, which were electromagnetic in nature, would literally cause objects to squash as they pushed against the ethereal medium. It was a physical distortion of matter moving through an absolute space, not a revelation that space and time were relative. He had one foot in the new world but kept his philosophical weight firmly planted in the old. He was so deeply committed to the Newtonian picture of a universe with a fixed, universal clock and a rigid, invisible grid of absolute space that he couldn't take the final, logical leap. His work was a masterful rearrangement of the furniture in the old house of physics, when what was needed was to realize the house itself had no foundation. This distinction is everything. Lorentz provided the how but completely missed the why. He gave physics the mathematical machinery that would later become the engine of special relativity, but he failed to understand what that machinery was actually for. He saw his equations as a description of what happens to objects within space, not a description of space and time themselves. His loyalty to the existing paradigm of the ether was so strong that it acted as a conceptual ceiling, preventing him from seeing the vast, new cosmological landscape that his own math had just revealed. He was like a cartographer who had perfectly drawn a map of a new continent, but insisted it was just a slightly different projection of the old world. The tragedy of Lorentz's near miss is its sheer proximity to the truth. He was standing right at the threshold of the greatest revolution in physics since Newton. All the pieces were there in his own work, yet he couldn't bring himself to cross over. It took a younger, less established thinker, unburdened by the same reverence for the old doctrines, to look at the same equations and see not a complex conspiracy to hide the ether, but a simple, elegant, and universal principle. The laws of physics, including the speed of light, are the same for all observers in uniform motion. There is no privileged frame of reference. Albert Einstein, in his Annus Mirabilis of 1905, took Lorentz's ingenious fix and transformed it from a mathematical curiosity into a profound statement about the fundamental fabric of the cosmos. He realized that space and time were not separate, absolute entities, but were woven together into a single, flexible fabric called space-time, where measurements of length and duration depend entirely on your state of motion. Lorentz had the keys to the kingdom but was too hesitant to turn the lock. After revolutionizing our understanding of space, time, and gravity, Albert Einstein turned his monumental intellect toward the grandest puzzle of all, the universe itself. In 1917, just 2 years after publishing his theory of general relativity, he set out to do what no one had ever done before: apply his equations to the entire cosmos. The result should have been his most stunning prediction yet. His field equations described a dynamic, living fabric of space-time, molded by the matter within it. When he solved them for the whole universe, the math spoke clearly and unambiguously. The universe could not be static. It had to be either expanding or contracting. It was inherently unstable, destined to change over time. This result flew in the face of everything astronomers believed at the time. The prevailing view, inherited from Newton and reinforced by centuries of observation, was of a stable, eternal, and essentially unchanging universe. The stars were fixed in their places, and the overall structure was considered permanent. For Einstein, this created a terrible conflict between the beautiful, relentless logic of his mathematics and the accepted wisdom of observational science. Rather than trusting the revolutionary implications of his own theory, he made a fateful choice. He modified his equations, inserting a new term, a fudge factor he called the cosmological constant. This was a repulsive force, a kind of anti-gravity that worked on the largest scales to perfectly balance the attractive pull of all the matter in the universe, propping it up into a state of perfect, eternal stillness. With this artificial adjustment, he forced his dynamic equations to describe a static, finite cosmos, one that matched the scientific consensus of the day. It is a moment of profound and deeply human irony. The man who had the courage to overturn Newton's absolute space and time, who trusted pure thought over established doctrine to redefine reality, suddenly lost his nerve when faced with the cosmological implications of his own work. He was swayed by a powerful philosophical bias, a desire for an eternal, unchanging universe that had been a bedrock of scientific and philosophical thought for millennia. He later called the introduction of the cosmological constant the biggest blunder of his life, and for good reason. Just over a decade later, Edwin Hubble's observations of receding galaxies would provide irrefutable evidence that the universe is indeed expanding, exactly as Einstein's original, unaltered equations had predicted. He had been handed the keys to the future of cosmology on a silver platter, and had thrown them away because he didn't like what they unlocked. This near miss is perhaps the most poignant in our entire story because it came from the one person who was best equipped to see the truth. It stands as a powerful lesson that scientific progress requires more than just brilliant mathematics. It demands the courage to follow those equations wherever they lead, even when they point to a reality that is strange, uncomfortable, and utterly at odds with our deepest intuitions. Einstein's genius gave us the tools to understand an expanding universe, but his own human inclination for stability and permanence temporarily blinded him to his greatest discovery. He had the expanding universe in his grasp years before anyone else, and he let it slip away, a testament to the fact that even the most revolutionary minds can sometimes be prisoners of their time. While Einstein was wrestling with his own equations, a brilliant and tragically short-lived Russian mathematician and meteorologist named Alexander Friedmann was approaching the problem from a completely different angle. Working in the tumultuous aftermath of the Russian Revolution, far from the major scientific centers of Europe, Friedmann did something that required immense intellectual courage. He took Einstein's published equations of general relativity and simply removed the cosmological constant. He trusted the raw, unadulterated math. What he found in 1922 was breathtaking. The equations did not describe a single, static universe. Instead, they painted a picture of a dynamic, living cosmos, one that was filled with possibilities. Friedmann's solutions showed that the universe could be expanding, flying apart from a dense beginning. It could be contracting, collapsing inward under its own gravity, or it could even be oscillating, forever breathing in and out in an endless cycle of cosmic death and rebirth. Furthermore, the fate of the universe was tied directly to its density and its geometry. A dense universe would have positive curvature, folding back on itself like a sphere. A less dense one would have negative curvature, splaying open like a saddle, and a perfectly balanced universe would be flat, adhering to the rules of Euclid on the grandest scale. This was the first complete, mathematically rigorous framework for a modern cosmology, a set of blueprints for the entire universe that is still used today. Yet, this monumental breakthrough was met with a deafening silence. Friedmann published his work in a German physics journal, but it was a relatively obscure publication, and his ideas were so radical that they were easily dismissed or simply overlooked. The scientific community, still heavily influenced by Einstein's authority and the deeply ingrained desire for a stable cosmos, was not ready to entertain the idea of a universe with a beginning or an end. It sounded too much like metaphysics, not physics. Even Einstein himself initially reacted with skepticism, briefly dismissing Friedmann's work as mathematically suspect before later conceding it was correct. This collective indifference created a delay of several years, a period where cosmology could have leaped forward, but instead remained stuck in the paradigm of a static, eternal universe. Friedman's near miss is a stark lesson in the sociology of science. A revolutionary idea is not enough. It needs to land in a community that is prepared to hear it, delivered through channels that command attention. His physical and intellectual isolation meant his voice was a whisper in a room shouting about the ether and static models. Tragically, Friedman died of typhoid fever in 1925, just 3 years after his groundbreaking publication, and a few years before evidence would emerge to prove him spectacularly right. He never lived to see his theoretical models become the foundation of modern cosmology. His story is one of the great what-ifs of science. What if his paper had been published in a more prominent journal? What if he had been able to travel and champion his ideas personally? What if the scientific world had been less enamored with Einstein's static solution? The path to understanding the shape of the universe might have been dramatically shortened. Instead, his work languished, a hidden key to the cosmos waiting for someone else to turn it in the lock. That someone would not be a theorist but an observer, a meticulous astronomer at Mount Wilson who was about to make the most important observational discovery in the history of cosmology. High atop Mount Wilson in California, Edwin Hubble was doing something no human had ever done before. He was measuring the universe with the most powerful telescope of its time. He peered into the depths of space, not just to catalog new stars, but to find a new cosmic rhythm. He was building on the work of Henrietta Leavitt, who had discovered that a certain kind of star, a Cepheid variable, could be used as a standard candle. Its intrinsic brightness was revealed by its pulse, allowing anyone who could measure its apparent brightness to calculate its distance with stunning accuracy. Hubble used this key to unlock the cosmos. He found these pulsing stars in mysterious, fuzzy nebulae and made a monumental discovery. These were not clouds of gas within our own Milky Way. They were entire other galaxies, vast islands of stars separated by unimaginable gulfs of empty space. The universe had suddenly grown exponentially larger. But Hubble's most shocking revelation was still to come. By combining his distance measurements with spectroscopic data, mostly collected by his colleague Milton Humason, he noticed something peculiar. The light from these distant galaxies was not arriving as it was sent. Its wavelength was stretched, shifted toward the red end of the spectrum. This redshift was a familiar phenomenon, a Doppler effect similar to the drop in pitch of a receding ambulance siren. It meant these galaxies were moving away from us, and the farther away a galaxy was, the faster it was receding. This was Hubble's law, a direct, linear relationship between distance and velocity. The inescapable conclusion was that the universe itself was expanding, like dots on an inflating balloon, all moving away from one another. It was the single most important observational discovery in the history of cosmology, and it finally provided the evidence that vindicated Friedman's theoretical models and forced Einstein to abandon his cosmological constant. Yet, in a twist of fate, the man who discovered the expansion of the universe himself failed to grasp its deepest implication. Hubble was first and foremost an observer, a master of meticulous measurement. His genius lay in collecting and analyzing data, not in speculative theorizing. He interpreted his groundbreaking discovery within the only geometric framework he knew, the flat, infinite, static stage of Euclidean and Newtonian space. In his mind, the galaxies were simply rushing apart through this absolute, pre-existing void. He saw the expansion as motion within space, not an expansion of space itself. This critical distinction meant he never fully connected his observation to the revolutionary physics of Einstein's general relativity, which described how matter and energy could warp the very fabric of the cosmos, giving it a shape and a geometry. This was Hubble's profound near miss. He had the most crucial piece of the puzzle in his hand, but he didn't realize it was the key to a much larger picture. He provided the what the universe is expanding, but he left the why and the how to the theorists, and those theorists for a time were slow to connect the dots. They were now armed with both a theory that predicted a dynamic universe, general relativity, and observations that confirmed it, Hubble's law. The next logical step was to ask what this expansion implied for the overall shape of everything. Was the universe expanding because it had positive curvature, flying apart from a big bang? Or was it negatively curved, destined to expand forever into a cold, empty void? Or was it perfectly flat, balanced on a knife's edge? Hubble's data was the starting gun for this new race to understand cosmic geometry, but he himself remained firmly in his lane as an observer, leaving the profound theoretical implications for others to unravel. His legacy is a powerful reminder that even the most earth-shattering discovery can be just the beginning of the story, and that the divide between seeing something and truly understanding it can be the widest chasm of all. As the astronomical community grappled with the staggering reality of an expanding universe, a new generation of theorists began asking the obvious next question: if everything is flying apart, what did it look like when it was all together? In the 1940s, a brilliant and colorful physicist named George Gamow, along with his students Ralph Alpher and Robert Herman, took on this challenge with breathtaking audacity. They turned the cosmic clock backward, imagining a time when the entire universe was compressed into an incredibly hot, dense state, a primeval fireball. Their work gave birth to what we now call the Big Bang Theory, and in doing so, they made one of the most spectacular predictions in the history of science. They calculated that the immense radiation from this initial explosion would have filled the entire cosmos, and as the universe expanded and cooled over billions of years, this light would have stretched from visible wavelengths into the microwave part of the spectrum. It would now permeate all of space as a faint, cold glow, a cosmic background radiation with a temperature of just a few degrees above absolute zero. They had, in essence, predicted the existence of the cosmic microwave background, the afterglow of creation itself. This was a monumental intellectual achievement, a bridge from theoretical speculation to observable reality. Yet, in a pattern we have seen before, their focus was remarkably specific. Gamow and his team were primarily fascinated by the problem of nucleosynthesis, how the elements were forged in the first few minutes of the universe. They brilliantly worked out how hydrogen could fuse into helium and trace amounts of other light elements in the intense heat of the early cosmos, and their calculations matched the observed abundances in the universe almost perfectly. This success, however, became a kind of intellectual gravity well, pulling their attention away from the other profound implications of their own theory. They viewed the predicted background radiation primarily as a byproduct, a leftover echo of the hot beginning. It did not occur to them that this faint glow could be much more than a simple confirmation of a hot past. It could be a detailed cosmic blueprint. The near miss here is one of unimaginable potential. Gamow and his colleagues had the key insight but failed to grasp the full lock it could open. They did not pursue the detailed properties of this predicted radiation. They never calculated what tiny, microscopic fluctuations in its temperature might look like, or how those fluctuations could be imprinted by the very shape and density of the universe. They overlooked the fact that the geometry of the cosmos, whether it was positively curved like a sphere, negatively curved like a saddle, or perfectly flat, would leave a distinct fingerprint on this radiation. A curved universe would focus the light, creating larger hot and cold spots. A flat universe would produce a very specific pattern of smaller variations. The cosmic microwave background wasn't just a relic. It was the ultimate cosmic messenger, carrying encrypted information about the overall curvature, composition, and fate of everything. By not chasing these implications, Gamo's team left a treasure map half unfolded. This hesitation created a vacuum, an opening for a compelling alternative. While Gamo was championing a universe with a definite beginning, other scientists, including Fred Hoyle, Hermann Bondi, and Thomas Gold, found the idea philosophically distasteful. They proposed the elegant steady-state theory, which argued that the universe had no beginning and would have no end. To account for the expansion observed by Hubble, they suggested that new matter was continuously being created in the empty space between galaxies, just enough to maintain a constant average density over time. It was a beautiful, eternal model that avoided the theological connotations of a creation event. For a while, it was a serious contender, precisely because the Big Bang theory lacked its most definitive piece of evidence. Without anyone actively looking for the predicted cosmic microwave background, the steady-state model seemed just as plausible. Gamo's failure to emphasize the detectable nature of his prediction had, ironically, kept the door wide open for his competitors. The final irony is that when the cosmic microwave background was finally discovered in the mid-1960s, it was entirely by accident. Arno Penzias and Robert Wilson at Bell Labs were troubleshooting a persistent, annoying hiss in a giant radio antenna, a noise that seemed to come from every direction in the sky and refused to go away. They famously scrubbed bird droppings from the dish, convinced the problem was terrestrial, only to eventually realize they were listening to the faint whisper of the universe's birth. They had stumbled upon Gamo's predicted echo. This accidental discovery instantly vindicated the Big Bang theory and effectively ended the debate with the steady-state model. But the story of the CMB was far from over. Its initial measurement only confirmed its existence and rough temperature. The far more difficult task, reading the intricate patterns within that glow to decipher the universe's true shape, would become the next great challenge, a pursuit that would itself be filled with its own series of misinterpretations and tantalizing near misses, as the next generation of cosmologists learned that having the right evidence is only half the battle. You also need to know how to read it. Just as the idea of a universe with a definite beginning began to gain traction, a powerful counter-argument emerged that appealed to a deep-seated desire for cosmic permanence. The steady-state theory, championed by the charismatic Fred Hoyle and his colleagues Hermann Bondi and Thomas Gold in the 1940s and 50s, was not just a scientific model, it was a philosophical statement. It proposed a universe that was eternal and unchanging in its overall appearance, even as it expanded. To solve the puzzle of galaxies moving apart, they introduced a truly radical idea: the continuous, spontaneous creation of matter. Not in a giant explosion, but atom by atom, hydrogen nucleus by nucleus, in the vast empty spaces between galaxies. This trickle of new material would exactly compensate for the thinning caused by expansion, ensuring the average density of the cosmos remained constant forever. It was an elegant, self-regulating universe with no need for a beginning or an end, a concept that felt satisfyingly complete to many. The theory's allure was immense. It was beautifully simple and avoided what some scientists saw as the unscientific, almost theological overtones of a cosmic genesis event. Hoyle, a master of public communication, famously coined the term Big Bang during a radio broadcast in 1949, intending it as a dismissive caricature of the idea he opposed. Ironically, the name stuck, but his own model captivated a significant portion of the scientific community for nearly 2 decades. It spurred fantastic debates and drove important theoretical work, precisely because it was a serious, well-formulated challenger. The competition between the two models forced cosmologists to sharpen their arguments and seek definitive observational tests, a process that ultimately strengthens science. However, this very elegance became the steady-state theory's fatal flaw. Its proponents were so committed to the beauty of an eternal, self-sustaining cosmos that they began to overlook or explain away mounting evidence that didn't fit their vision. The first major clue was the work of people like George Gamow on nucleosynthesis. The Big Bang model predicted that the early universe would have been a nuclear furnace, fusing hydrogen into about 25% helium with trace amounts of other light elements. When astronomers looked out at the oldest stars and primordial gas clouds, that's exactly what they found. This universal abundance of helium was very difficult for the steady-state model to explain, as it relied on stars alone to produce all the elements, a process far too slow and inefficient to account for the sheer volume observed. Hoyle and others worked valiantly to tweak their model, but it started to require increasingly complex and unconvincing adjustments. The second, and ultimately decisive, clue was the one Gamow had predicted but hadn't emphasized enough: the cosmic microwave background radiation. The steady-state universe, being eternal, had no hot, dense beginning. Therefore, it could not have a leftover thermal echo permeating all of space. When Penzias and Wilson accidentally discovered this faint microwave hiss in 1965, it should have been the immediate death knell for the theory. Yet, its defenders were initially reluctant to surrender. They proposed alternative explanations, suggesting the radiation might be coming from undiscovered astronomical sources within a steady-state framework, like a haze of heated interstellar dust. But as observations improved, it became clear the radiation was too uniform and too perfectly matched the predicted temperature of a primordial fireball. The evidence was overwhelming. The universe had indeed had a hot, dense beginning. This near miss is a classic example of how a compelling narrative can sometimes hold more power than contradictory data, at least for a time. The proponents of the steady-state theory were not poor scientists. They were brilliant thinkers captivated by a beautiful idea. Their adherence to that idea created a kind of confirmation bias, leading them to minimize the significance of the helium abundance and to grasp at straws when the CMB was discovered. They missed the clues because they were not just looking for answers, they were looking for answers that supported their preferred version of reality. The decline of the steady-state model finally cleared the way for the Big Bang to become the standard model of cosmology, but it left a crucial question wide open. If the universe began in a hot Big Bang and has been expanding ever since, what is the overall geometry of that expansion? Is space curved by the matter within it, and if so, how? Answering that question would require not just accepting the beginning, but reading the fine print left behind from that first moment. The discovery of the cosmic microwave background was a monumental triumph, the smoking gun that finally settled the great debate and crowned the Big Bang as the reigning model of our universe. Scientists everywhere breathed a collective sigh of victory. They had found the primordial echo, and it was real. But in that moment of celebration, a new, more subtle mystery was being born. The initial measurements of this faint glow revealed something that was, frankly, a little too perfect. The radiation was incredibly uniform, arriving from every direction in space with almost exactly the same temperature, to within a few thousandths of a degree. This extreme isotropy, this smoothness, was deeply puzzling. On the surface, it seemed to suggest a universe that was homogeneous and simple, but this very simplicity began to feel like a problem. How could a universe that started in a hot, dense state and expanded for billions of years end up so perfectly even? Where were the seeds, the tiny initial irregularities that would have eventually grown under gravity into the vast cosmic structures we see today, the galaxies, clusters, and superclusters? The unsettling smoothness of the CMB was a clue that something was missing from the story. The immediate and seemingly logical interpretation of this smoothness was that it pointed toward a specific geometry, a perfectly flat universe. The mathematics of general relativity showed that the density of matter and energy in the cosmos directly warps its spatial curvature. There is a critical density that acts like a cosmic balancing point. If the universe had more than this critical density, it would have positive curvature, folding back on itself like a sphere. If it had less, it would have negative curvature, splaying open like a saddle. But if it had exactly the critical density, space would be flat, adhering to the rules of Euclid on the grandest imaginable scale. The remarkable uniformity of the early CMB measurements within their fairly large error bars was consistent with this perfect, flat balance. It was an elegant solution, and many cosmologists began to lean toward the idea that we indeed lived in a universe with zero curvature. The case, it seemed, was nearly closed. This conclusion, however, was a spectacular near miss, a classic example of being right for the wrong reasons. The problem wasn't the math, it was the resolution. Those early instruments, for all their ingenuity, were like trying to judge the smoothness of a sheet of ice by looking at it from a mile away. It might appear perfectly flat and featureless, but get up close with the right tools, and you'd see a complex landscape of tiny ripples, bumps, and fractures. The early CMB experiments simply lacked the sensitivity to detect the incredibly faint anisotropies, the tiny variations in temperature from one patch of the sky to another. These fluctuations, predicted by theory to be there, were the true cosmic blueprint. Their specific pattern, their angular size and distribution, would be the definitive signature of the universe's geometry. A flat universe would produce a very distinct pattern of spots, while a curved universe would warp and magnify that pattern in a unique way. By not seeing any fluctuations, scientists mistakenly interpreted the data as evidence for flatness, when in reality, their tools were just too blunt to see the intricate details that would have revealed the full, nuanced truth. This premature consensus had a real cost. It created a period of complacency, a sense that the major questions about the large-scale structure of the universe were essentially answered. The focus shifted away from designing experiments specifically to hunt for these tiny wrinkles, delaying the development of the exquisitely sensitive technology needed to find them. For nearly 2 decades, cosmology was held back by this oversimplified picture. The lesson here is profound and echoes throughout the history of science. The absence of evidence is not evidence of absence. Sometimes the most important discoveries are not the loud, obvious signals, but the whispers hiding just below the threshold of our perception. Approximate data can be seductive because it often fits neatly into our existing models, reinforcing our preconceptions and obscuring the deeper, more complex reality waiting to be uncovered. It would take a new generation of thinkers and a bold, space-based mission to finally listen for those whispers and hear the true shape of the universe speaking through the static of creation. Just as cosmologists were settling into the new Big Bang paradigm, a set of nagging, fundamental questions refused to go away. If the universe began in a hot, dense state, why was it so incredibly large and uniform? Why did opposite sides of the cosmos, regions that could never have been in contact with each other, look exactly the same? And most perplexing of all, why did the early geometry of the universe appear to be balanced so perfectly on a knife's edge between eternal expansion and catastrophic collapse? These weren't minor curiosities, they were deep cracks in the foundation of the model, known as the horizon problem, the flatness problem, and the magnetic monopole problem. The universe, as observed, seemed too fine-tuned, too homogeneous, to have arisen from a simple explosive beginning. The solution arrived in a flash of insight from a young physicist named Alan Guth in the early 1980s, and it was so radical it redefined the concept of a beginning itself. He proposed a breathtakingly brief but unimaginably violent event called cosmic inflation, a period of hyper-exponential expansion that occurred in the first tiny fraction of a second after the Big Bang. In this fleeting moment, a patch of space smaller than a subatomic particle was stretched to a size larger than our entire observable universe today, smoothing out any initial wrinkles and driving its geometry toward perfect flatness with incredible precision. This was a theoretical masterstroke of the highest order. Inflation didn't just solve one problem, it solved them all in a single, elegant framework. The reason the universe appears so uniform is because it all came from a tiny, connected region that was inflated to cosmic proportions. The reason space appears so flat is the same reason the surface of a balloon looks flatter and flatter as you blow it up to an enormous size. Inflation stretched the fabric of space-time so tremendously that any initial curvature became imperceptible to us. The theory made a firm, testable prediction. The universe must be flat, or so very nearly flat that any deviation would be incredibly difficult to detect. It was a bold claim, one that gave cosmologists a specific target to aim for. Yet, in the years immediately following Guth's proposal, a curious hesitation set in. The prediction was clear, but the technological capability to test it with the required precision felt like a distant dream. The tiny temperature fluctuations in the cosmic microwave background that would confirm a flat universe were estimated to be variations of just 1 part in 100,000, a level of sensitivity far beyond what any instrument of the early 80s could achieve. This gap between brilliant theory and practical verification created a period of suspended animation in cosmology. The inflationary paradigm was so compelling, so mathematically beautiful, that it gained widespread acceptance on theoretical grounds alone. Many researchers began to treat a flat universe as a foregone conclusion, a solved problem on the blackboard, even though no telescope or satellite had yet provided the hard evidence. This intellectual comfort zone became its own kind of near miss. With the answer seemingly in hand, the urgent, driving need to mount a definitive observational campaign to measure the universe's curvature lost some of its momentum. Funding and resources for the next generation of ultra-sensitive SIMBI experiments were slower to materialize than they might have been if the theoretical stakes were higher. Furthermore, the focus remained narrowly on confirming flatness, which discouraged the broader exploration of alternative models of curvature that inflation had ostensibly ruled out. What if the theory was slightly wrong? What if the universe was only approximately flat or had a more complex topology that inflation couldn't account for? These questions were not pursued with the same vigor because the elegant solution already seemed to be in place. This delay between prediction and proof represents a critical juncture where confidence in a beautiful idea temporarily outpaced the messy, demanding work of empirical validation. It underscores a subtle trap in scientific progress. The power of a compelling narrative can sometimes make the search for confirming evidence feel almost redundant. The story of inflation was so good that it felt true, and in science, that feeling can be a dangerous substitute for data. It meant that for over a decade, the precise geometry of the universe remained in a kind of quantum state, both known and unknown, its truth waiting for technology to catch up to imagination. The stage was indeed set for projects like COBE and its successors, but they were launched into a scientific culture that already knew what it expected to find, a preconception that would itself shape how the first tantalizing data was interpreted, leading to the next chapter of near misses in our eternal quest to map the ultimate structure of reality. After years of theoretical anticipation, the moment of truth finally arrived with the launch of the Cosmic Background Explorer, or COBE, satellite in 1989. This was not just another space mission. It was humanity's first dedicated attempt to read the universe's oldest light with the seriousness it deserved. The scientific community held its breath, waiting to see if the primordial whisper of the Big Bang would finally reveal its secrets. When the initial data streamed back, it was met with a wave of euphoria and relief. COBE had done it. It had captured the cosmic microwave background in stunning detail, and its most headline-grabbing result was the breathtaking smoothness of that radiation. The temperature was uniform across the sky to within 1 part in 100,000, a finding that seemed to shout from the rooftops that the predictions of inflation were correct. The universe appeared to be perfectly flat, its geometry balanced on the precise critical density that theorists had dreamed of. It was a moment of triumph, a seeming confirmation that we finally understood the fundamental shape of everything. The COBE team, led by George Smoot and John Mather, would eventually receive the Nobel Prize for this monumental achievement, and for a time, it felt like a major chapter in cosmology had been decisively closed. Yet, beneath the celebratory headlines and the Nobel glory, a more nuanced story was unfolding, one of limitations and overlooked possibilities. While COBE was a giant leap forward, it was also a product of its time. Its instruments were pioneers, but they had their constraints. The satellite's resolution was relatively coarse. It could only see the sky in large patches about 7 degrees across. To put that in perspective, that's roughly the width of your fist held at arm's length. This was like looking at a priceless, intricate tapestry from across a vast room. You could clearly see its overall color and texture, confirming it was indeed a tapestry, but you were completely missing the intricate stitches, the subtle variations in thread, and the tiny, telling details that revealed the artist's true intent and technique. COBE saw the broad, smooth canvas of the early universe, but it was blind to the all-important tiny wrinkles, the anisotropies, that were predicted to be there. This lack of fine detail is where the near miss occurred. In their justified excitement over confirming the overall flatness, many researchers transitioned from treating inflation as a compelling theory to treating it as an established fact. The COBE data was so consistent with a flat universe that the scientific conversation quickly narrowed. Alternative ideas that the universe might have a very slight positive curvature, folding back on itself ever so gently, or a hint of negative curvature, splaying open just a fraction, were largely pushed to the sidelines. Even more exotic possibilities, like a universe with a multiply-connected topology that might act like a cosmic hall of mirrors, were seldom discussed in mainstream circles. The data was good, but it wasn't that good. It couldn't definitively rule out these fascinating, if fringe, scenarios. The celebration of success inadvertently created a kind of intellectual complacency, a consensus that discouraged the deeper questioning of what other stories the CMB might be trying to tell. COBE had answered the big question, but in doing so, it made everyone forget to ask the next dozen smaller, more precise ones that were essential for a complete understanding. The legacy of COBE, therefore, is beautifully paradoxical. It was both a spectacular success and a subtle diversion. It provided the first clear, clean map of the early universe, banishing any last doubts about the Big Bang and handing a major victory to the theory of inflation. But its limitations meant that the universe's geometry was still not pinned down with absolute certainty. The satellite had drawn the outline of the cosmic blueprint in thick, bold marker, but the all-important fine print, the instructions that would dictate the ultimate fate of everything, remained blurred and unread. This moment teaches a critical lesson about the nature of scientific progress. Every answer, no matter how profound, is merely a prelude to a more refined set of questions. Cope's triumph was not an endpoint. It was the starting gun for a new race, a challenge to the next generation to build instruments with sharper eyes, to look closer at the tapestry, and to discover that the universe's true shape was a story far richer and more complex than anyone had yet imagined. Buoyed by the triumph of Cope, the next generation of cosmologists knew exactly what they had to do next. They needed to get closer to the tapestry, to see the individual threads of the cosmic microwave background. But building another multi-million-dollar satellite mission would take years, even decades, so they turned to a more daring, nimble, and almost romantic approach, sending their instruments to the very edge of space beneath massive, high-altitude balloons. In the late 1990s, two pioneering projects named Boomerang and Maxima undertook this audacious task. They were launched from the frozen, desolate expanse of Antarctica, where the stable polar winds could carry them on a long-duration flight in a wide circle, high above the distorting blanket of Earth's atmosphere. Their goal was simple yet profound: to capture a sharper image of the infant universe than had ever been seen before. The results, when they came, were nothing short of spectacular. Boomerang and Maxima delivered with breathtaking clarity. Their maps of the CMB were like switching from a blurry, impressionist painting to a high-definition photograph. For the first time, scientists could clearly see the tiny temperature variations, the hot and cold spots, that were the seeds of all future structure in the cosmos. The most celebrated finding was the precise measurement of the largest of these spots, known as the first acoustic peak. Its angular size on the sky was a direct measuring stick for the geometry of the universe, and it pointed unequivocally toward flatness. The data was a resounding confirmation of the inflationary paradigm, and it made front-page news around the world. It felt like the final, definitive piece of the puzzle had been slotted perfectly into place. The universe was flat, the story was over, but for a handful of attentive researchers, that wasn't the whole story. Buried within the exquisite data were a few faint, subtle whispers that didn't quite fit the clean, simple narrative of a perfectly flat cosmos. The patterns of the smaller spots, the second and third acoustic peaks, seemed slightly off. Their power, their intensity, was not quite what the most straightforward models of a flat universe predicted. It was as if the cosmic orchestra was playing the right melody, but a few instruments were slightly out of tune. These minuscule anomalies were so small they could easily be dismissed as statistical noise, the inevitable background fuzz of any incredibly precise measurement. And that is exactly what most of the scientific community did. The evidence for flatness from the first peak was so powerful and so expected that these smaller glitches were filed away as curiosities, not clues. The desire for a clear, elegant answer, a universe with exactly the critical density, was so strong that it created a powerful bias against alternative interpretations. This collective decision to overlook the anomalies represents a critical near miss. Those faint signals were not mere noise. They were the first hints of a richer, more complicated cosmic reality. They could have been interpreted as evidence that the universe was not perfectly flat, but possessed a tiny amount of positive curvature, making it ever so slightly closed. Or perhaps they pointed toward something even more exotic, like a multiply-connected topology where space folds back on itself in a complex finite shape, like a cosmic donut. Such a universe could still appear mostly flat on the largest scales, while having a profound and fascinating structure on scales beyond our observational horizon. But these possibilities were largely left unexplored. The scientific momentum was entirely behind the flat universe model, and questioning it based on such minor discrepancies seemed like nitpicking. The lesson here is a painful one in the history of science. The gravitational pull of a dominant paradigm can be so strong that it bends the interpretation of data itself, causing researchers to dismiss the very clues that could lead to a deeper understanding. Boomerang and Maxima had provided not just an answer but also a question, and in the rush to celebrate the answer, the question was tragically ignored. These balloon-born pioneers had flown to the edge of space and brought back a map that was both triumphant and tantalizingly incomplete, a promise that the true geometry of our universe might still hold mysteries waiting for an even more powerful eye to uncover. Building on the high-resolution glimpses from balloon-born experiments, the scientific community was ready for a definitive answer, and the Wilkinson Microwave Anisotropy Probe, or WMAP, was designed to provide it. Launched in 2001, this sophisticated spacecraft was a monumental leap beyond COBE, equipped with technology so precise it could map the cosmic microwave background's temperature fluctuations down to millionths of a degree. For 9 years, it patiently scanned the heavens, and the treasure trove of data it beamed back felt like the culmination of a century of cosmological inquiry. The results were a resounding victory for the prevailing model. WMAP measurements of the acoustic peaks in the CMB were exquisitely detailed, providing overwhelming support for a universe that is geometrically flat and governed by the lambda-CDM model, a framework where cold dark matter provides the cosmic scaffolding for galaxies and a mysterious dark energy drives an accelerating expansion. The parameters were pinned down with unprecedented accuracy. We now knew the age of the universe to within 1% and its composition to a fraction of a decimal. It was a triumph of observational science, a seemingly complete and final picture of our cosmic home. Yet, within this stunningly precise map, there were strange, faint fingerprints that didn't quite fit the beautiful frame. The most famous of these became known as the axis of evil, a name that perfectly captured its unsettling and mysterious nature. This was not a feature of the small, hot and cold spots that seeded galaxies, but a bizarre, large-scale alignment in the CMB. The fluctuations seemed to be correlated across vast swaths of the sky in a way that defied the core cosmological principle, the idea that the universe should be roughly the same in all directions, with no preferred axis or special center. It was as if the cosmos had a faint but undeniable north and south pole, a fundamental orientation that simply shouldn't exist. Other curious glitches appeared too, like an unexpected cold spot and a puzzling hemispheric asymmetry, where one half of the sky seemed slightly different from the other. For a small group of researchers, these weren't just minor statistical flukes, they were potential clues to a far more fascinating reality. Perhaps the axis of evil was a signature of a universe with a non-trivial topology, a shape that wasn't just simply flat and infinite, but one that was finite and multiply-connected, like a hall of mirrors or a cosmic donut where space wraps around on itself. In such a universe, light could travel along these wrapped dimensions, creating patterns and correlations on scales larger than our observable horizon. These anomalies could be the faint echoes of that larger structure, a glimpse of the overall shape of reality beyond our local patch. It was a breathtaking possibility, one that promised to rewrite our understanding of the cosmos entirely. But the overwhelming majority of the cosmology community saw these features differently. They were deeply invested in the spectacular success of the standard lambda-CDM model, which explained 99.9% of the data with breathtaking accuracy. To them, these large-scale anomalies were almost certainly just artifacts, the result of subtle systematic errors in the instrument's calibration. or the statistical luck of the draw in a universe that is, after all, just one single realization of a random process? The path of least resistance and the most scientifically conservative approach was to attribute them to noise and focus on the magnificent consensus story. Dedicating significant resources to investigating what were likely just ghosts in the machine seemed like a distraction from the real work of refining the already successful model. This collective decision to largely dismiss the anomalies represents a profound near miss in the modern era of cosmology. It wasn't a failure of data or technology, but a failure of imagination driven by the powerful inertia of consensus. The tension between building a robust standard model and entertaining fringe possibilities is a necessary part of science, but there is always a risk that the weight of the consensus can prematurely crush interesting, if unorthodox, ideas. By not pursuing these oddities with the same vigor as the main results, scientists may have missed an early opportunity to peer into the true, and perhaps far stranger, geometry of the cosmos. WMAP legacy is therefore beautifully dual-natured. It provided the most compelling evidence yet for a flat, dark energy-dominated universe, while simultaneously leaving behind a handful of whispering, unanswered questions that continue to hint that the final chapter on cosmic geometry has not yet been written. If WMAP gave us a high-definition map of the early universe, then the Planck satellite, launched in 2009, was designed to be the ultimate cosmic cartographer, equipped with instruments of almost unimaginable sensitivity. For over 4 years, this European Space Agency observatory collected data, measuring the faint whisper of the cosmic microwave background with a precision that was nothing short of breathtaking. It was the most advanced effort yet to answer the ultimate question: what is the precise shape of our cosmic home? The results, when they were finally released, were a monumental achievement. Planck's data constrained the curvature of the universe to be astonishingly close to zero, confirming with greater certainty than ever that we live in a cosmos that is, for all practical purposes, geometrically flat. This was hailed as the final, definitive nail in the coffin for any significant curvature and a crowning validation of the inflationary Big Bang model. But buried within the terabytes of exquisitely precise data was a tiny, tantalizing ghost in the machine, a whisper that didn't quite fit the triumphant narrative. Some analyses of the Planck data, particularly when combined with other cosmological probes, revealed a very slight but persistent preference. The universe didn't appear to be perfectly flat. It seemed to hint at a minute positive curvature, suggesting a cosmos that is ever so gently closed, like a sphere of unimaginable size. The statistical significance was faint, hovering right at the edge of what could be dismissed as a random fluctuation, but it was there, a persistent signal in the noise that refused to completely vanish. This wasn't a discovery, but it was an intriguing, unresolved note in an otherwise harmonious symphony of data. The reaction from the broader cosmology community, however, was largely to explain it away. The standard model, the lambda-CDM framework that had been so spectacularly successful, strongly predicts a flat universe. The concept of inflation, which had solved so many puzzles, drives the geometry toward perfect flatness with incredible force. Faced with a minor discrepancy, the most logical and scientifically conservative conclusion was to attribute it to a combination of measurement uncertainties, subtle systematic errors in the incredibly complex data analysis, or just plain old statistical chance. The weight of the existing paradigm was so immense that this faint signal was downplayed, treated as a curiosity rather than a clue. The near miss here is not in the data itself, but in our response to it. There was a palpable reluctance to seriously entertain the profound implications of what even a minuscule amount of curvature would mean, because the consequences would be staggering. If the universe has a positive curvature, no matter how slight, it would be finite in volume. It would mean that if you could travel in a perfectly straight line for long enough, you would eventually return to your starting point, not because you turned, but because space itself gracefully curves back on itself. More importantly, it would pose a direct challenge to the simplest versions of cosmic inflation. For inflation to produce a universe with even a hint of curvature, the inflationary period would have to be fine-tuned in a very specific way, forcing a major rethink of our most cherished theory of the very beginning. This tiny anomaly wasn't just a statistical blip, it was a potential key to a much larger, more complex cosmic story. Planck's ultimate legacy, therefore, is beautifully paradoxical. It was both a triumph of precision cosmology, seemingly closing the book on curvature, and a subtle, humble reminder that the universe always has another card up its sleeve. It delivered an answer so precise that it revealed the next, more nuanced question. The satellite didn't fail. It succeeded so well that it showed us the limits of our current understanding and the incredible refinement required for the next leap. It proved that science is not a march toward final answers, but an endless process of calibration and questioning, where even our most definitive measurements contain the seeds of the next great mystery. The quest to understand the shape of everything continues, and future observatories will now be tasked with hunting down that faint ghost of curvature, knowing that the biggest surprises often hide in the smallest of signals. While we've been gazing at the ancient light of the cosmic microwave background, a parallel revolution has been unfolding much closer to home, in the relatively recent universe of galaxies and cosmic structures. This 24th near miss doesn't come from the faint echo of the beginning, but from the vibrant, sprawling cosmic cities that fill the space around us. To understand the shape of the universe, cosmologists realized they needed not just one measuring tape, but many, each checking the other. One of the most powerful of these tools relies on a fossilized echo from a much earlier time, an imprint left on the distribution of galaxies known as baryon acoustic oscillations. Imagine the early universe as a hot, dense soup of particles and light. In this primordial plasma, gravity tried to pull matter together into clumps, while the immense pressure of radiation tried to push it apart. This created powerful sound waves, spherical pressure waves, that rippled outward through the boiling chaos. But when the universe was about 380,000 years old, it cooled enough for atoms to form in an event called recombination. The light suddenly broke free, becoming the cosmic microwave background we see today, and the sound waves instantly froze in place, their progress halted. They left behind a subtle, spherical shell of slightly denser matter at a very specific distance from the center of each initial ripple, a distance that became a universal standard ruler, exactly 500 million light-years long. Billions of years later, as galaxies formed, they did so preferentially on these frozen shells. This means that if you map the positions of millions of galaxies, you don't just see a random scatter. You can detect a faint statistical preference for galaxies to be separated by that specific 500 million light-year scale. By measuring the apparent size of this standard ruler in the sky at different distances, and thus different eras of the universe, we can track how the expansion of space has stretched it over time. This gives us a direct measurement of the universe's expansion history and, crucially, its geometry. If the universe is flat, the ruler will appear the same angular size in every direction. If it's curved, the apparent size will be distorted in a specific, predictable way. Early large-scale galaxy surveys, like the Sloan Digital Sky Survey, began to map these baryon acoustic oscillations in the early 2000s. The results were incredibly exciting and seemed to provide powerful, independent confirmation of what the CMB was telling us. The BAO signal was clearly detected, and it strongly supported a geometrically flat universe, beautifully aligning with the lambda CDM model. It felt like another case closed, a triumphant convergence of evidence from two completely different cosmic epochs. But this very success contained the seeds of the near miss. Those initial BAO measurements, while groundbreaking, were based on a few 100,000 galaxies. The signal was strong, but the resolution was coarse. The error bars on their measurements were just large enough to comfortably encompass a perfectly flat universe, but they were also large enough to hide subtle deviations. The scientific narrative at the time was one of convergence and confirmation, so there was little incentive to go looking for phantom discrepancies in the data that everyone agreed was pointing toward a clear answer. Furthermore, the BAO technique was often used in combination with other probes like the CMB to constrain the cosmological model. This cross-checking is a pillar of good science, but it can sometimes create a situation where the probes begin to talk to each other in a way that masks their individual weaknesses. A slight tension between them can be smoothed over by the combined statistical analysis, hiding a potential clue that one of them might be seeing something the others are not. The most prominent example of this is what we now call the Hubble tension, a growing discrepancy between the measured expansion rate of the universe in the local, modern era and the expansion rate inferred from the CMB in the early universe. While not a direct measurement of curvature, the Hubble constant is deeply intertwined with the overall cosmological model, including geometry. Early on, some hints of this tension were already present in the data, but they were largely dismissed as systematic errors in one method or the other. The clean, flat universe picture from the combined BAO and CMB data was so compelling that it overshadowed these nascent inconsistencies. Researchers were, understandably, more focused on building a coherent story than on picking at its potential loose threads. They were using a powerful standard ruler, but they were reading its markings with a degree of confidence that its precision at the time might not have fully warranted. They missed the opportunity to ask if the very geometry they were assuming might be slightly wrong, and whether that could be the source of the other tensions beginning to simmer beneath the surface. This illustrates a profound challenge in modern cosmology. When multiple lines of evidence seem to agree, it's incredibly difficult to remember that they might all be agreeing on a slightly incorrect answer, and that the truth might be hiding in the tiny, overlooked spaces between the data points. And so we arrive at the present moment, standing on the shoulders of all the giants who came before, armed with technology that would seem like pure magic to every thinker on our list. We have space telescopes like the magnificent James Webb peering back to the dawn of the first galaxies, and we have a new generation of ground-based observatories like the Simons Observatory and the future CMB-S4 project, designed to map the cosmic microwave background with a precision that would have been unimaginable just a decade ago. These are not just tools, they are time machines and cartographic instruments of unparalleled power, built to finally answer the ancient question of our cosmic shape with absolute, unassailable certainty. The ambition is breathtaking, and the potential for discovery is limitless. We are, by any measure, in a golden age of cosmological inquiry. Yet, even as we point these incredible instruments at the heavens, we must confront a subtle and deeply human danger, one that has derailed discovery countless times before. Our experiments, for all their technological marvel, are not designed in a philosophical vacuum. They are constructed to test very specific predictions born from our current, best theories. We are hunting for the faint signatures of inflation, for the specific patterns of a flat universe, for the subtle effects of dark energy as described by our lambda CDM model. In essence, we are building exquisite traps designed to catch the universe behaving exactly the way we expect it to. We input our assumptions, our priors, into the very heart of our data analysis pipelines. We tell our algorithms what to look for, and in doing so, we might be unconsciously telling them what to ignore. This is the preemptive near miss of our generation, a risk that is not about flawed data or limited technology, but about constrained imagination. What if the universe is not just flat, but has a more complex topology, like a three-dimensional torus or a twisted, multiply-connected space where if you could travel far enough in one direction, you'd return to your starting point from another? Such a cosmos could perfectly mimic a flat universe on the largest scales we can currently observe, its telltale wraparound signatures existing just beyond our observational horizon. Our current models, with their built-in assumption of simple, infinite flatness, are not primed to look for these ghosts in the machine. We are so focused on confirming the beautiful story we've written that we might be deaf to the universe trying to tell us a different, far stranger tale. The history of science, as our journey has vividly shown, is not a straight line of accumulating facts. It is a story of revolutions, of paradigm shifts that occurred precisely when someone dared to question the very foundations of what everyone else knew to be true. From Copernicus moving the center to Einstein unifying space and time, the greatest leaps forward came from asking not just how the universe works within our model, but whether the model itself was the right one. The danger today is that our models have become so successful, so mathematically elegant and empirically powerful, that they have gained an air of invincibility. To question them can feel like heresy, a waste of time better spent on refining the details. But this is the siren song of complacency. The universe has consistently proven to be more inventive, more bizarre, and more wonderful than our brightest minds could ever anticipate. The James Webb Space Telescope might see something peculiar about the very first galaxies that doesn't fit the standard timeline of structure formation. The next-generation CMB experiments might detect correlations between temperature fluctuations on scales that are supposedly causally disconnected. These anomalies will be small, buried in the noise, and the immediate instinct will be to attribute them to systematic error or to tweak the existing model with a new parameter. But will we have the courage, the intellectual humility, to entertain the far more radical possibility? Will we allow ourselves to ask if these glitches are not flaws in the data, but the first faint fingerprints of a cosmic architecture we haven't even begun to dream of? The quest to understand the shape of the universe is far from over. In fact, with every answer, we simply reveal a deeper layer of questions. Future scientists will likely look back at our era not as the time we finally figured it all out, but as another chapter filled with its own brilliant, tantalizing near misses, moments when the truth was right in front of us, waiting for someone to finally see the world with new eyes. Looking back across this extraordinary tapestry of human inquiry, a powerful pattern emerges from these 25 near misses, a pattern that reveals less about the universe's shape and more about the shape of our own understanding. One of the most persistent threads is the profound influence of philosophical and cultural bias. From Aristotle's perfect spheres to Einstein's static universe, we see brilliant minds constrained not by a lack of intelligence, but by a deep-seated desire for a cosmos that is orderly, eternal, and centered on humanity. These weren't just scientific models, they were reflections of the philosophical aspirations of their time, comforting narratives that placed us at the heart of creation. This desire for comfort and order acted as a powerful filter, causing generations of thinkers to dismiss evidence that pointed toward a messier, more dynamic, and far less human-centric reality. It's a humbling reminder that even our most objective scientific pursuits are never entirely free from the silent whispers of our hopes and fears. Equally telling is the recurring gap between theoretical brilliance and observational capability. Bernhard Riemann gave us the mathematical language for curved space decades before physics had any use for it. George Gamow predicted the cosmic microwave background but lacked the technology to go looking for it. In both cases, the tools to test a revolutionary idea simply didn't exist, leaving these breakthroughs to languish as abstract curiosities. Conversely, we have moments where the observations were clear, but the theoretical framework to interpret them was missing. Edwin Hubble saw the galaxies fleeing from us, but he interpreted their flight through the old Newtonian idea of motion through absolute space, not as an expansion of space itself. The history of cosmology is a long, slow dance between theory and observation, where sometimes one partner leads and the other follows, and true progress only happens when they finally move in sync. And we cannot overlook the sheer role of chance and communication in this story. Alexander Friedman's expanding universe solutions were published in an obscure journal and ignored, partly because he was isolated from the main scientific currents of his time. If his paper had landed on Einstein's desk with a passionate cover letter, or if he had lived longer to champion his own work, the course of cosmology might have accelerated by a decade. Similarly, the mathematical tools of non-Euclidean geometry were sitting on the shelf, fully formed and waiting, while physicists struggled to explain the Michelson-Morley results with increasingly clumsy concepts like the ether. It shows us that science is not a perfectly logical march toward truth. It is a deeply human endeavor, subject to the vagaries of reputation, geography, and simple bad luck. A great idea is not enough. It needs to arrive at the right time and find an audience ready to hear it. Yet, for all these stumbles and wrong turns, the most important lesson is that none of these episodes were true failures. Each near miss, each wrong turn was an essential step on the path. Ptolemy's complex epicycles were a dead end, but they represented a centuries-long effort to make predictions match observations, honing the scientific skill of model building. The long detour into the ether, while ultimately misguided, led to the exquisite precision of the Michelson-Morley experiment and the mathematical innovations of Lorentz, which in turn provided the very tools Einstein would use to build special relativity. Even Einstein's cosmological constant, his so-called biggest blunder, has been resurrected in modern times as the leading candidate for the dark energy that accelerates the universe's expansion. An idea isn't wrong, it's just often premature, a piece of a puzzle whose full picture isn't yet visible. This journey grants us a vital perspective on our own place in the history of knowledge. The certainties of today will inevitably be seen as the limitations of tomorrow. The flat, dark energy-dominated universe of our current lambda-CDM model feels like a complete picture, but it is almost certainly just the best version of the truth we have for now. The anomalies in the Planck data, the tensions in our measurements of the Hubble constant, these are not nuisances to be explained away, but likely the faint signals of the next revolution, the clues that will force our grandchildren's generation to see the cosmos in a way we cannot yet conceive. The pursuit of the universe's shape is therefore more than a technical challenge. It is the ultimate expression of human curiosity and resilience. It is a story not of a destination, but of an endless, inspiring process of learning, correcting, and learning again. A testament to our unshakable desire to understand our place in the grand scheme of things. From the perfect spheres envisioned by the ancients to the breathtakingly precise flatness charted by our most advanced satellites, this entire journey reveals a truth far more profound than any single answer about cosmic geometry. It shows us that the very heart of science is not a destination, but a process, a relentless, self-correcting dance between bold imagination and meticulous observation. Each of these 25 near misses was not a failure, but a vital step. They were the necessary wrong turns that illuminated the right path, the brilliant ideas that were just a little too early or a little too shackled to the paradigms of their time, yet each one provided an essential piece of the grand puzzle. What these stories teach us is that the pursuit of knowledge is a deeply human endeavor, filled with all our brilliance and all our biases. We see the courage to challenge authority, from Copernicus moving our planet from the center to Hubble revealing an expanding cosmos. But we also see the powerful grip of comfort, from the long-held belief in a static, eternal universe to the reluctance to abandon the ether. These episodes remind us that progress demands more than just intelligence. It requires the humility to question our own assumptions and the resilience to follow the evidence wherever it leads, even when it points to a reality far stranger and more wonderful than we ever imagined. Now, as we stand on the shoulders of all these giants, we look forward with tools like the James Webb Space Telescope and next-generation observatories, equipped with the hard-won lessons of history. We know that our current map of a flat, dark energy-filled universe is the best we have, but we also know it is almost certainly incomplete. The faint anomalies in our data, the lingering tensions between measurements, these are not frustrations, but the very clues that will guide the next revolution. The greatest surprise may not be that we were wrong about the shape of the universe, but that its true geometry is something we haven't even begun to conceive. So the quest continues, not as a search for a final answer, but as an eternal conversation with the cosmos, a testament to our unending curiosity and our place within this magnificent, mysterious reality. Thank you for sharing this journey through the near misses that have defined our cosmic story. If you've enjoyed exploring these twists and turns of discovery, be sure to like this video, subscribe for more deep dives into the mysteries of the universe, and let us know in the comments which of these near misses you find the most fascinating.